Hello everyone. Our topic for today is all about isomorphism and automorphism. Yours truly, Brian Yap Donke. Our lesson objectives: at the end of the discussion, students should be able to first differentiate isomorphism and automorphism. Second, determine if two groups are isomorphic or not. So, what is automorphism? In mathematics, an automorphism is an isomorphism from a mathematical object to itself. It is, in some sense, a symmetry of the object and a way of mapping the object to itself while preserving all of its structure. The set of all automorphism of an object forms a group called the automorphism group. So, a homomorphism is a function between groups that preserve the group's structure in each group. It's a tool for comparing two groups for similarities. Sometimes, two groups are more than just similar, they're identical. In this case, we no longer call function a homomorphism. Instead, we call it an isomorphism, and we say that the two groups are isomorphic. Let's give a precise definition an isomorphism. Suppose that we have two groups, J and H, and a homomorphism F from J to H. So, recall that a homomorphism is a function f such that f of x times y is equals to f of x times f of y. Now, a homomorphism does not have to be one-to-one. It does not have to be an injection. Now, a homomorphism does not have to be one-to-one. It does not have to be an injection. It's possible for many elements in J to map to the same element in H. Similarly, if F does not have to be onto, it does not have to be a surjection, but for the groups J and H to be identical, we need the homomorphism F to be one-to-one and onto. If needs to be both an injection and interjection. In this way, we can pair each element in J with a unique element in H, and vice versa. An isomorphism is a homomorphism that is one-to-one and onto, and also an isomorphism is a homomorphism and bijection. So, our first example, consider the groups of the positive real numbers under multiplication and all real numbers under addition. One homomorphism between them is a logarithm function. We can check that this is a homomorphism by using the laws of logarithms, log from J to H. So, log x times y is equals to log x plus log y. To see if this is an isomorphism, we have to test if it's a bijection. Let's first check that this function is one-to-one. Suppose that log x is equals to log y. So, since the log s are equal to e to each power is equal to So let's simplify. So this will become x is equals to y. Next, the range of the log function is all real numbers. So this function is on top. So in this example, the log of function is a homomorphism and a bijection that makes it an isomorphism. These two groups are isomorphic. So in example number 2, non-zero complex numbers under multiplication, which we denote by a C with a multiplication. This sign here, it's understood that you are not including 0 because 0 does not have an inverse under multiplication. And complex numbers z with absolute z is equals to 1 under multiplication. We denote this group by s to the power of 1. This standard notation when talking about n-dimensional spheres. The s short for sphere and the 1 tells us the dimension. So in this case, s to the power of 1 is just the circle in the complex plane with a radius of 1. Recall that every complex number can be written in polar form as r times to the I theta, where r is the distance of the complex number to the origin, and the theta is now 4. You have to rotate from the positive x-axis to reach the complex number. With this setup, we can now define a homomorphism between these two groups. So f c to the power of x to s to the power of 1, the function is f of r times e to the I theta equals e to the I theta. So you can visualize this by taking any non-zero complex number z, drawing away from the origin to z, and mapping z to the point where it intersects s to the power of 1. But is this a homomorphism? Let's check. So f c to the power of x to s to the power of 1, and f r times e to the power of I theta is equals to e to the power of I theta. So if we have z is equals to r times e to the power of I alpha, and w is equals to s times e to the power of I beta. So this will become f z times w and f z times f of z times f of w. So this will become r times e to the power of I alpha times s times e I beta is equals to f of r times e I alpha times f of s times e I beta. So this will become f of r times s times e to the power of I times alpha plus beta is equals to f of r times e I alpha times f of s times e I beta. So this will become e to the power of I alpha plus I beta is equals to e to the power of I alpha times e to the power of I beta. So in this solution, we can say that this is a homomorphism. It is also onto because for every point in the circle, there are an infinite number of complex number which map to it, but for the same reason, this function is not one-to-one. So, while this is a homomorphism, it is not an isomorphism. So, that would be all. Thank you.